Hey guys, welcome back to day 5, concentration. So today we're going to talk about the units of concentration, right? And for our purposes, it's going to be solution concentration. And remember that it is a ratio, right? Ratio of, right, solute to solvent, or solute to volume. Okay, we're going to talk about 4 of them. 4 units of concentration, when they're used, and some of the things about them. Okay, so it's a ratio, and we use these ratios so we can, again, measuring amounts and whatnot. And so the first unit that we've used in Chem 1, we're going to continue to use, is molarity. Molarity, capital M, right? And it's mole per liter. Now, it's moles of solute per liter of solution, which is the total volume. And we like molarity. It is by far the most common. Right? The problem is it is temperature dependent. And why it's temperature dependent is because volume is temperature dependent. All right? A lot of substances they expand with increasing temperature and they contract with decreasing temperature. All right? Solids do it, liquids can do it, gases can do it. And so the sidewalk cracks there in your driveway and they're expansion joints so that the sidewalk can expand when it gets hot and cool down when it gets cold, right? Or shrink when it gets cold. Well, liquids the same way. Liquids are the same way. Water expands when it gets hot and contracts, so it's temperature dependent. So this is why your temperature matters. But it's by far the most common because it's the most easiest to use, right? Now, some of the things, right, we also have, it's moles per liter, but it's also millimoles per milliliter, right? Millimoles per milliliter. You just divide them both by 1,000. So if I have, it's no different if I have 0.004 moles over 0.025 liters is the same thing as 4 millimoles over 25 milliliters, right? It's the same math. Okay, and we can easily measure the volume in milliliters or even liters, and we get the moles. Volume times molarity is moles. Reactions happen in moles, so we like molarity. Okay, so it's moles per liter. It's temperature dependent. The second one that we'll introduce this chapter is molality. Molality, and that's a lowercase m. A lot of times it's italicized in the book. And that is mole per kilogram. Now it's mole of solute per kilogram of solvent. So it's mole per kilogram. Now this one is temperature, and you guessed it, independent. And it's temperature independent because mass is temperature independent, right? Your mass does not change with temperature. Okay? Now, some of our masses may change with season, right? Especially with Thanksgiving, Christmas. Some of us partaking a little too much. But mass does not change with temperature. Okay? Now, we do not use this, so this is not used, right? Unless the experiment involves a temperature change. Which, if it involves a temperature change, it makes sense that we would use a temperature independent, ratio of solute to solvent, instead of molarity, where it is temperature dependent. Right? Because your molarity is going to change with temperature. If you go from 5 degrees Celsius to 75 degrees Celsius, your volume changed quite a bit, actually. So, all right, we will use that. Now, for dilute solutions, if we're dilute, all right, really dilute, our molarity and molality tend to be very close to each other. As we get more and more concentrated, they veer. They start to separate, diverge. All right, third one. Mass percent. Mass percent. All right, so what is this? This is mass per mass. So it's mass of solute to mass of solution, total solution, right, times 100%. And this, of course, is temperature independent again, because mass is independent. All right, so mass percent, and a lot of times we use this for IVs. Mass is very easy to measure, very accurate to measure. So mass percent is the way we're going to do it. Now, there's two parts, or two subparts of mass percent: parts per million and parts per billion. So there's parts per million, which is ppm, and parts per billion, which is ppb. Sorry, I put B first. ppb. Right? So it's the same thing. It's mass of solute over mass of solution times 10 to the 6 for a million, and mass of solute over mass of solution times 10 to the 9th. All right, so these are very, very dilute solutions, and they're parts per million, parts per billion. We use those for dilute solutions, especially if you get a water bill every year. They should give you a report saying what's in the water, right? What they test for. There's probably even more things that it's probably scary. I do recommend filtering tap water. I do. All right, and so mass percent. Water is such a good solvent, guys. It's such a good solvent. A lot of things dissolve in it. All right, so we've got mass percent. Last one, mole fraction. Mole fraction. We use the Greek letter chi. Looks like an X. The mole fraction of gas I, or I, whatever. It's usually for gases, but it can be for anything. But it's a particle ratio. It's moles of whatever I is, the solute, but it doesn't have to be the solute. But moles of I all over total moles. All right, so sometimes we need to use the mole fraction. A lot of times with pressures, we will do that because, pressure, ideal gas law, P, V, and T all can vary, right? So, well, if two of those variables are changing, the pressure and the temperature are changing, all of a sudden now, what do we do, right? The moles, the particles, that particle ratio is what we have, all right? So those are the four units we'll use, and after this chapter, molarity will be the main one, but all four of these will use this chapter, and